We would now like to calculate the electric potential difference between 2 points in space for a simple point charge, QS. Now here, this charge could be positive or negative. And I'm going to consider a path that goes from A to B, 2 points in space. And I'd like to consider some arbitrary point on that where our electric field, here I'm imagining that the electric field is positive, and I have a little ds. And our definition for potential difference between these 2 points is equal to minus the integral of from A to B of the electric field of this source dotted into ds. Now, once again, we want a good coordinate system that will match this problem. We'll imagine our origin. So we're going to choose an origin where the source is, and our unit vector will point radially outward. So we'll have an r hat and a theta hat. And here, this is RA, and this is RB, and that's R. So now, in this coordinate system, we know that the electric field of a point charge is just QS over R squared R hat. And the displacement ds in this coordinate system, well, we've talked about this before when we had work, but we'll just imagine again that if you displace a little bit this way and then a little bit that way, where you have some angle d theta, and over there is dr, then our displacement vector can be thought of as a radially outward part and a tangential part. But the tangential part won't make any difference because the dot product of r and theta hat is 0. And so once again, only the radial part matters. And what we get here is the integral VB minus VA is the integral as our variable r goes from RA to RB. This dot product is KQS r squared dr. And now this integral dr over r squared is minus 1 over r, so there's 2 minus signs. So they come out, and we get KQS 1 over RB minus 1 over RA. And that is the potential difference in space between these 2 points for the point charge. But this result is the starting point for what we'd like to do to define a potential function. Now, let's imagine that instead of going to 2 arbitrary points, we started at RA equals infinity. And we have a charge QS that's at the origin. And we're taking a path that goes from infinity to a distance r away from QS. So that's our path. So here we have RB equals R. Well, we've done the calculation. We don't have to do it again. And so we see that our result is that the potential difference, V of R minus V of infinity, well, is equal to KQS 1 over R minus 1 over infinity. And 1 over infinity is 0. 1 over R minus 1 over infinity. And so we get that V of R minus V of infinity is equal to KQS over R. Now, this is a very important function. What does this quantity KQS over R actually mean? And in words, remember, this is negative of the work done in taking a test charge from infinity to a distance r away divided by the test charge. And so we can say that this quantity is the minus of the electrical work if we started a test charge at infinity and brought it to a distance r away from our original source, minus that work divided by the test charge. We also could have said it was equal to the change in potential energy divided by the test charge. If we started with a test charge at infinity, and we had our source here, and we moved our test charge so that it's a distance r away from the source in our final state, and we calculated the change in potential energy divided by Q test, that's exactly what that quantity is.